Hey friends, let's do some chapter 9 practice problems. Before we go into the actual practice problem set, I wanted to go through a couple naming questions with you guys. So let's start over here. We know that alcohols have the all suffix, and we know that the alcohol is usually the priority group, and so we want to make sure when we're numbering our chain, our alcohol is on the smallest number possible. So for example, if I were to number this chain, I have two options. I could use the green path or the yellow path. I would clearly want to use the green path because we want the OH on the smallest number possible. So let's get rid of the yellow. Next thing, we see that it is a four-membered chain. So we're going to call that a butane. And if we're calling that the parent chain, we're going to call this and this a substituent. And we're going to call the alcohol a substituent. We know that the alcohol is at 1, and we would call it an all. And on 3, we have a dimethyl. So if we put those things together, we get 3,3-dimethyl butane 1 all. This is technically the most correct IUPAC way to write it. You could also choose to omit the 1 because it is on position number 1, so you don't have to put it there. But this is technically the most correct IUPAC way. Next up, let's do one like this. And now we actually have 2 alcohols. So let's do all the possible paths. We could do 1, 2, 3, 4. We could do 1, 2, 3, 4. Or we could even do 1, 2, 3, 4, right? So one thing I want to mention with this one is we could not use the pink path because we want to choose the longest chain possible that has the OHs directly on it. So if we were to use the pink path, the OH would be bonded to a carbon and that whole group would be a substituent, and we don't want that. So now between green and blue, we kind of run into a problem because we have an O on number 4 and an O on number 1, regardless of which direction we go. So the big deciding factor here will actually be this methyl. So we want to go the path that has the most substituents on the lowest numbers. So if we start with the green path, we have an OH at 1, a methyl at 2, and then an OH at 4. And that's much better than having an OH at 1, a methyl at 3, and an OH at 4. So let's get rid of the blue path. Again, we know that this is a butane. We also have a 2-methyl. And there's a couple different ways we can name this. We're going to say it's a 2-methyl butane 1,4-diol. You could have also said 2-methyl 1,4-butadiol. Diol just means we have 2 alcohols. 1,4 tells us the position. We could have either put 1,4 in the middle here or at the end here. Doesn't matter, both are correct. I believe this one is the most correct IUPAC way, but meh. Alrighty. So I think that's good enough for naming, so let's move right along. All right, so we have this question right here that is a good chapter 11 question. So when we have a nucleophilic addition to a carbonyl, right, what the heck does that mean? Well, we've seen this in both our reduction reactions and our Grignard reaction. So let's say we have a ketone, right? And we're doing a reduction, right? So this is going to be a nucleophilic attack. And since it gets added to the carbonyl, we call that a nucleophilic addition. And we know that we're going to end up with an alcohol and a hydrogen, right? So this carbonyl carbon went from sp2 to sp3. And that is going to be the answer for this kind of question. Okay, so he could give you a question like this that's kind of like Orgo 1 review, but it's one of those silly questions that you might not be prepared for, but it's supposed to be like an easy kind of question. So it's asking which does not represent a pair of resonance structures. So for resonance structures, we know that we're moving electrons around. So here, we could just move this double bond, and we would get this next structure, a positive charge here, and our double bond here. That works out. Now, as far as our radical goes, we could have movement like this, where one electron from the double bond and one electron from the radical will form a new double bond here and leave one radical by itself on the other carbon. So both of these guys check out so far. All right, so this double bond could move here. And if we do that, we get rid of the plus charge here and we add it right here. So this does count as resonance. And now we do a similar kind of thing where we go from this plus charge to this plus charge, except they're just trying to trick you with this question because we have no electrons moving around. They just somehow plucked the charge and changed it. So that one does not count as a resonance structure. It is not a valid pair. All the other ones do check out. Now here we have a really fun kind of protecting group question. So let me write that down. The concept it's questioning you on is protecting groups. And so first of all, we see mesylate. He made it easy, so you don't have to know what this thing is. He tells you it's mesylate. And now we know that mesylate acts as a protecting group. And what it usually does is takes an alcohol and it's going to keep the stereochemistry and it's going to add the mesylate group onto the oxygen. All right, cool. What about the other chiral center? What happens here? Well, absolutely nothing. This only reacts with the alcohol, so we want a final answer that does not touch this carbon center. Let's just make sure. This checks out, checks out. This does not check out. We cross it out because what did it do to this carbon center? All right, next thing. We know that in this second step, NaI is going to be an SN2 reaction where it replaces the OMS with an I. And we started out with wedged. Mesylate will leave it wedged, but the SN2 reaction should switch it and make it dashed. So let's see which one of these guys has a dashed iodine. Nope. Yes. And then what the heck even is this? No, we hate it. So 2 is the only answer choice that makes sense here. And that's it. So for a question like this, we can look at it and we automatically know it's a Grignard reaction because of this magnesium. So I'm going to write Grignard. And all the N and O represent here are like steps of the reaction. So it's not a nitrogen and an oxygen. It's just saying that N is the name of the intermediate, O is the name of the product. All right, so for a question like this, if we see the magnesium with ether, we know that in that step we're forming our Grignard. And I will show you two ways to do this. So I like to draw things out. So 1, 2, 3, 4, 4-carbon chain. And we have a bromine here. So we have an alkyl halide. And I know once I react that with magnesium, I'm going to make the Grignard reagent, which looks like this. Cool. So this is going to be N. At this point, the Grignard reaction would usually be the Grignard reagent reacting with some kind of carbonyl, except here we don't have a carbonyl, we just have D2O, which is just like H2O. So instead of being some kind of Grignard reaction, this guy is just going to steal the deuterium, act like a base, and go on its merry way. So all we did is add a deuterium here. Cool, simple enough, right? This is one of those rare questions where I would say like you don't even need to bother drawing it out, only because if we zoom in here, if you guys can tell, okay, alkyl halide, I know to make the Grignard reagent, I just cross this off and give it a negative charge. And then at that point, I'm going to attack a deuterium. So we would just end up replacing that with a D. So you're just looking for the answer choice that replaced the bromine with a deuterium. If that's too complicated looking, that's totally fine. Just draw it out. It's not too crazy. So when we look at this, OD, no. OD, no. Why the heck is the deuterium all the way over there? No. And this doesn't even have a deuterium at all. That sucks. The only one that makes sense is answer choice B. And that's how you do a Grignard question. Yay. Alrighty, so this is a reduction question you could get. And the way I know it's automatically a reduction question is because of this reagent. So LiAlH4 is a reducing agent. And the question is asking which will not be reduced by LiAlH4. So let's think about this. What does get reduced by LiAlH4? Well, we know that this is going to reduce group 1, which is ketones and aldehydes. And it's also going to reduce group 2 because it is strong, and that consists of carboxylic acids and esters. So essentially, we're looking for the answer choice that is not a ketone, not an aldehyde, not a carboxylic acid, or not an ester, because we know those guys do get reduced. So answer choice A, this is just an alkene. We're pretty sure that's the right answer, but let's just double check. Here we have an aldehyde. Here we have a carboxylic acid. Here we have an ester. And here we have a ketone. So I am going to write those out for you because it is important that you are familiar with those functional groups and seeing it in this condensed formula. So just kind of know what each of these condensed formulas stand for without having to draw it out. Okay, but back to the question. A is the correct answer because alkenes are the only answer choice here that are not going to be reduced by LiAlH4. And that's pretty much all you need to know for a question like this. here we have a fun naming question, and so I'm going to write over here, benzyl alcohol, just so I can scroll down. So, benzyl alcohol. This is a really important concept because students tend to mix up benzyl and phenyl groups because they do look so similar. So a benzyl alcohol has a bend in it. So the squiggly line represents where it attaches to any chain, right? And so it attaches with a bend, aka a CH2, whereas a phenyl attaches directly at the ring. So I'm going to say phenyl, benzyl. So we're looking for benzyl alcohol. This one is directly attached to the ring, therefore that is a phenyl. This is a phenyl and it has this group on there. This one is just not even an alcohol. What the heck, bro? So now we're stuck between this, which has the bend, so that's benzyl. And then this has a bend, but it also has a CH3. Why would we? Who knows? So the correct answer here is 2. That is the only correct benzyl alcohol. Yay! So another reduction question, I should say. Which of the correct reagents would do this reaction? Whatever, right? First thing you have to notice is here we have a ketone. And here we have a CO2CH3. Now, if you have trouble visualizing what that looks like, it looks like this. So this is an ester. All right, so we know that ketones and aldehydes are part of group 1. We know that esters and carboxylic acids are group 2. We also know that group 1 is more reactive, and therefore it can use either reagents. Group 2, however, is less reactive and can only use LiAlH4. So this is important because in the final product, we actually have reduced both functional groups to an alcohol. In order to reduce both groups, we have to use LiAlH4. So this is the correct answer. If we had only reduced this guy and left this one an ester, we know that we would have used NABH4. And then C is just a trick. Just there to distract you and trick you. Ta-da! So it's pretty straightforward. You just have to know which reagent does what and which carbonyl does what. Alrighty, so here we have yet another reduction question. The reason I know it's a reduction question is because NABD4, that's just NABH4. I'm so sorry. NABH4, all he did is replace the hydrogens with deuteriums, and the reason he does this is to kind of see if you know what goes where, right? So the deuterium is going to be the one that does the attacking. So we end up adding a deuterium. So I'll keep it like this just so it's easier to see. So the deuterium is going to slide right in here. And then this oxygen is going to become single bonded with a negative charge. And at this point, we have H2O. So when it steals a hydrogen, it becomes OH. So we get CH3, CD, CH3, OH. And the trick here is some students would have mixed up where the deuterium goes. Maybe deuterium goes both places, but we know deuterium is the one that did the attacking, and then the protonating was done by the water. So our correct answer is OH with the deuterium. That's B. The reason this is wrong is because we have an OD, wrong. OD, wrong. Here, we don't have any deuterium, wrong. And here we have, what's going on? What's that mess? I don't know. Ew. So the correct answer is B. Ta-da! All right, so I'm going to leave you guys off with a Grignard question. And we're going to say which of these Grignard reactions would fail to occur as written. And for this, you have to remember that the Grignard reaction does not work with acidic protons. What counts as an acidic proton? Well, carboxylic acids, triple bonds, and hydrogens on heteroatoms. Ta-da. So we're essentially looking for the answer choice that has either a carboxylic acid, a triple bond, or a hydrogen on a heteroatom. So let's zoom in. The first thing I see, this is just a straight carbon chain. This is just a straight carbon chain. Simple. The next thing I notice is alcohol, or oxygen at least. We have an oxygen. And now we have to figure out what functional group this is. Well, this looks like that. So this functional group is an ether, whereas this functional group is a carboxylic acid. There are no hydrogens directly attached to this heteroatom, so that one is good to go. However, this hydrogen on the carboxylic acid is going to be too acidic. It's going to count as an acidic proton, and this reaction will not happen. That's all I have for you today, friends. I hope these practice problems were helpful. Please feel free to reach out to Katrina or me if you have any questions whatsoever.